Hey there, we're going to go over some conservation of momentum notes. Now in class we went through a few demos and then we also did some initial practice problems. And what we should have found is whenever we have a closed system, and remember a closed system just means that the net force on the system is equal to zero, that the momentum of that system is conserved. And that word there, conserved, really just means that it stays the same. So the overall momentum of your system is going to stay the same. Now don't get that confused with the momentum of each object within the system, because of the momentum of each object within the system can change, but overall as a system, it's going to stay the same. It's going to be conserved. So we can look at a little example. Let's say we have cart 1 that's moving with a velocity of 2 meters per second, and then we have another cart in the system that's moving with a velocity of 1 meter per second. And let's say the mass of each cart here is 1 kilogram. And they end up colliding, and the first cart, after the collision, slows down to 1 meter per second, and the second cart speeds up to a velocity of 2 meters per second. Now let's look at each cart individually and then the system as a whole. So cart 1 initially has a momentum 1 kilogram times 2 meters per second, which is just 2 kilograms times meters per second. And cart 2 initially has momentum 1 kilogram times 1 meter per second. So that's 1 kilogram times meters per second. And after the collision, cart 1 now has momentum 1 kilogram times 1 meter per second. So it has 1 kilogram times meters per second. And cart 2 has momentum 1 kilogram times 2 meters per second. So 2 kilograms times meters per second. So each individual cart, the momentum of them has changed. So we went from 2 kilograms times meters per second to 1 for cart 1, and we went from 1 kilogram times meters per second to 2 kilograms times meters per second. So each individual cart has changed, but as a system, before the collision, the system had 2 kilograms times meters per second plus 1, so 3 kilograms times meters per second. And the momentum of the system afterwards, again, we just add those up, and it still equals 3 kilograms times meters per second. So the momentum of your system stayed the same, but the momentum of each individual object, it changed. And so that's the whole idea of conservation momentum. So as a system, it's going to stay the same afterwards. The individual objects may change, but as a system as a whole, that stays the same. And so as we kind of get a little further in studying these different types of collisions and interactions with objects within a system, we're going to have to end up classifying these different types of interactions. And really, we're going to have 4 different ones. We're going to have an explosion, an elastic collision, an inelastic collision, and then lastly, we'll have a completely inelastic collision. Now, in all these cases here, your momentum is going to be conserved. So P is conserved. So regardless of the different type of interaction or collision, your overall momentum of the system is going to be conserved. And in order to classify these different types of collisions here, we have to go one step further. We have to go in and look at the energy of the system and see what's happening. Now, next unit, or next semester, I should say, we're going to spend a whole unit going in and looking at the different types of energy and some calculations and things like that. And for this unit here that we're in and trying to classify the different types of collisions, we're really just kind of focused on one type of energy, and that is kinetic energy. And so you need to be able to calculate the kinetic energy of a system to see what kind of collision is taking place. And the kinetic energy is really just when we have motion taking place. So when you have objects in motion, then you have kinetic energy. And our calculation for kinetic energy is K, kinetic energy, is equal to 1/2 mv squared. And so your mass is your m, and that's in kilograms. The v is your velocity, and that's in meters per second. And so the unit here for kinetic energy, what we're left with is we have kilograms times meters squared per second squared, which is equal to a joule, a capital J there. So you need to be able to calculate the kinetic energy of the different objects in the system to classify what type of collision that we have. And so we'll kind of run through here and we'll look at the different types of collisions. So when we have an elastic collision, your momentum is conserved. And in addition to this, the kinetic energy of the system as a whole is conserved. When you have an inelastic collision, again, your momentum is conserved. But the energy of the system is not conserved. So an example of these two, let's say I have two carts. Okay, one's moving with a velocity v, and then another cart is moving with a velocity. We'll call this v1 and v2. They collide, and afterwards they have some new velocity. Okay, so we'll say v prime here and v prime here. And so the momentum of your system before equals the momentum of the system after. And then the kinetic energy of the system before also equals the kinetic energy of the system after. In this inelastic collision, it's very similar. Okay, you have two carts here, and they're moving, then they collide, and now they have a new velocity. And the only difference between these two is that the kinetic energy in this for your system is not conserved. So you're going to have a different kinetic energy for your system afterwards than you did before. And then the third type of collision that we'll look at is the completely inelastic. And in this type of collision, your momentum of your system is conserved. And so again, you can notice that your momentum is conserved, right, for all these different types of collision. And in this one, your kinetic energy is not conserved. So in two of these interactions or collisions, kinetic energy is not conserved. That's in your inelastic and your completely inelastic. And how we distinguish the difference between these two is what happens after the collision. So if I have two of these that are moving with a velocity and they collide, but after the collision they stick together. So now they're both moving with the same velocity, but they're stuck together. So they're kind of like one object together. And in that situation, that would be a completely inelastic collision because your kinetic energy wasn't conserved, which is why we'd say it's inelastic, but then they stick together. So then you have a completely inelastic collision. So we can look at an example real quick. Let's say that we have two carts and one cart is moving with a velocity of 2 meters per second. And then another cart is moving with a velocity of 1 meter per second. And then we have a collision here. And that cart 1 is now moving with a velocity of 1 meter per second. And cart 2 is moving with a velocity of 2 meters per second. And so we can look in and start calculating our kinetic energy for each object and for the system. And let's say that the mass here is still equal to 1 kilogram. So the kinetic energy of cart 1 would be 1/2 the mass, which is 1 kilogram, times its velocity squared. So 2 squared is 4, half of 4 is 2, so you have 2 joules. And the kinetic energy of cart 2, you have 1/2 the mass, which is 1 kilogram, times its velocity, which is 1 meter per second, that's squared, and you end up with 0.5 joules. So the kinetic energy of your system, we would just add them up. So that'd be 2.5 joules. And looking afterwards, the kinetic energy of cart 1 would be 1/2 the mass, which is 1 kilogram, times the velocity, 1 meter per second, and that's squared. You end up with 0.5 joules. And the kinetic energy of cart 2 is 1/2 your mass, 1 kilogram, times its velocity, 2 squared. So 2 squared is 4, half of that is 2. You end up with 2 joules. So the kinetic energy of your system afterwards is just 2.5 joules. And in comparing the kinetic energy of the system before and after, it stayed the same. So if I was asked to classify this collision, it would be an elastic collision. And the reason why I know it's elastic is because your kinetic energy of the system stayed the same. And so that's how we go through and we label these different types of collisions. We have to look at the energy of the system. What's happening? Is the energy conserved or is it not conserved? Are they sticking together? And that's how we classify these different types of collisions. But in all these different types of collisions, your momentum will always be conserved.